Okay guys, good morning. Let's get started. With any questions about this handout that I sent on Friday? Nope. Okay, I also sent out about reserving a classroom for Tuesday, 2:30 to 5 if you would like to use it for studying. A couple of people sent me emails about that. This is Allgood Hall in 126. If you'd like to study in that room, please send me an email. I prefer if you have multiple students, send me a group of names. And you're welcome to use that room, Allgood Hall in 126. It has desk, bench desk instead of individual desks, so you can spread out your books. Okay. In 126, but please send me your name if you plan on to use that room. Okay. We'll give this a try. You gotta be quiet over there, etc., or we'll get thrown out of there. Okay. Please send me an email if you want to use the room. Tuesdays, 2:30 to 5. Alkene reactions. Our warm-up, our outline, pink outline, and we were looking at reactions with X2 halogenation. This is off. Is it better off or on? Off. Okay, so this was the reaction with X2 chlorine or bromine. We talked about why do you only get trans? Okay, because it comes from backside attack of the bromonium ion or the chloronium ion. Any questions about the mechanism for a reaction with bromine or chlorine? We should have a quiz this week, by the way. Okay, next on the outline. By the way, what type of product does addition of halogen to an alkene give? What's the name of the product? It's more than just an alkyl halide because there's two halides. It's a dihalide. There's another term there, Roman numeral number 1. Vicinal. Yes, what does vicinal mean? No, what does vicinal mean? Anybody? Vicinal means the halogens are in the same, they're vicinity. Vicinity neighbors, they're neighboring, 1, 2. If they're on the same carbon, they're called geminal, twins. Vicinal. I'm sure vicinal's in your textbook, though. Okay, number 2, Roman numeral 2, under B. Addition of halogen in water to give what type of product? Halohydrin. Okay, so let's look at that. If you take an alkene reactor with halogen and include water, you don't get a vicinal dichloride. Instead, you get a product with a chlorine and an OH. And this is called a halohydrin. Halo for halide, hydrin like hydrate. It includes the OH. The reaction is going to be regioselective. You're not going to get this regioisomer. Mechanism. First reaction is formation of the chloronium ion. So we have our chlorine Electrons attack chlorine. Where are we going to leave cation, left or right? Left, attack chlorine. Kick off the leading group. Boom, boom, boom. Bond to chlorine. Kick off the leading group. It became the halide minus. Cation here. But is it really going to be a cation? Well, hopefully no, because we're under B, right? And these are reactions that do not involve a cation. What's going to happen here immediately? Back bonding. Okay? So the back bond, and what do we get? Get a chloronium ion. Is this really an intermediate? No, this is NaF. These first two steps happen at the same exact time. They're concerted. The only reason I'm drawing this on the board is so I can do it stepwise on the board, but I realize it really ain't stepwise in real life. The first intermediate is the chloronium ion. Now, if water wasn't there, Cl- would attack here, open it up, and you get a bisphenol dichloride. Whenever you have water present, though, it will be the nucleophile. Water will be the nucleophile. And it will attack. Where are we going to attack, left or right? Left, the same place as if it was here. Because this is going to strain. You put more strain and more partial plus here. That was talked about on the other page. Attack here, kick off the leading group. What does that give? Chlorine got kicked off, but it's still bonded over here. What's now bonded here? Oxygen, H, H, one lone pair plus charge. Because when water makes bond here, we do not lose an H. This is our product, except we just need to go neutral. We need to lose an H plus. What can take the H? Actually, Cl minus could, or water could. Take the H, these electrons move on to oxygen. What does that give? That gives final product plus what? HCl. HCl is actually the small molecule byproduct here. Hopefully that was really nothing much new, other than the idea that water can attack the chloronium or bromonium ion. It attacks the same place as if the halide had attacked. And we said if water's present, it's going to be the thing it attacks. Usually water is present in excess in this reaction, and you just have to just go with it that if water's present, it's going to attack. So, reaction of alkene with halide, with halogen and water. What does that give? Halohydrin. That's something good for a note card, right? Then mechanistic details. The mechanism is very similar to other. We'll see consistencies going forward. We do not get this. Why does the water not end up on the other carbon? Or the OH, which came from water? Because right here, which carbon does water attack? Attacks over here. We've already said why. And again, it's just like if it was here. But it doesn't attack a free cation. How do we know? Because if stereochemistry was involved here, we would not get both outcomes. We only get backside attack outcomes. So it has to, that means it comes from this. Now this product does not have any stereochemistry. We haven't learned that yet. And so you don't need to show any dashed revolt. That's why it's not shown. Later on we'll learn when do you need to show the dashed bold and when not. But there's no stereochemistry. There's no chirality. There's no difference. It's like if I came in here and drew a circle. I wouldn't say, hey, can you draw a left-handed circle? You would say, what do you mean? I don't know what that is. Because there's no such thing. But if I drew a hand on the board, there it is. I could say, well, hey, let's draw the right hand. And you would say, oh, okay, I understand, because there's another form. Well, there's no other form of that. There's no other form of that. So we'll have to learn when stereochemistry is important. Stereochemistry is actually important in this example here because of the ring. And the ring, as we move forward, we'll talk about why. So what do we got here? An alkene, bromine and water. What is that? Halohydrin? Yeah. Okay. This is actually your product. We'll do mechanism, but I'm going to do just to show intermediates. I'm not going to do arrow movement. Okay? What's the first intermediate that's formed here?
Swinging the pi bond down to bond one of the bromines?
Mechanistically, yeah. But what intermediate are you going to get to first? Well, that's actually good. It's actually good. Hey, let me draw it out because I know how to work like a math problem. Hey, what's 63 times 17? You would say, hey, well, let me work it out, right? I know how to work it out. That's actually good. There is a wee bit of memorization that needs to get you to prompted. Okay, a wee little bit. And the intermediate here is the bromonium ion. Yeah? It's just like the previous reaction. So a wee little bit of memorization. What's a bromonium ion going to look like? Well, let's draw it with stereochemistry. It's going to be bromine here, bromine, and a methyl there, right? Bromonium ion, where the bromine is added across the pi bond. But mechanistically, you should be able to get there. But what's the stereochemistry? Because here it actually matters. That's tetrahedral and that's tetrahedral. Tetrahedral, two in the plane, one forward, one back. So if we keep the two bonds of the ring in the plane, bond to the bromine is going to be forward or back. Let's make it go back. We could do both. If it goes back, that means the methyl is going to be what? Forward. Now the bromine is also bonded here. But is this bond going to be forward or back? Forward. It's going to have to be back. Why is it got to be back?
Same direction as the top bond.
Yeah.
Because you can't have a three-member ring trans. But also, what's the mechanism? Here's the alkene. Okay, this is forward to me. Let's pretend like you were flipped. You guys are behind the wall. Okay? This is behind this board, so I'm going to call this back. Okay? It's back, but I'm facing you guys. So, okay? The pi bond attacks bromine. And at the same time, what does bromine do? Okay, I attack you. What do you do at the same time? You back bond. Okay, both bonds are to the same side. They have to be. I attack bromine and you bond. Yeah, unless you're going to come around here, but how are you going to do that? Okay, they have to be on the same side because of the way it attacks and also a three-membered ring. So this came from where bromine was behind, the pi bond attacks bromine, and the bromine back bonded. Both bonds are back. That's a plus charge. But you can also get where both bonds to the bromine are forward. That would be if we call this forward. So I'm going to say plus enantiomer. And an enantiomer, as we will learn a little bit later, is where all your bonds are switched in terms of dashed or bold. The enantiomer would be where both of these are bolded, and that's dashed. That would come from where the bromine was on the other side, the forward side versus the back side. Okay? So it actually matters here. Now from here, how do you get final product? Water, right? Which carbon does water attack, top or bottom? Well, you see where the oxygen attack, but top, right? So that's where we're substituted. Okay? The bromine is back. So how does the water come in? It comes in and it kicks off the bond, but in terms of forward or back, the water comes in forward. And so we get, this just kicks off and it's still like that. The bond to the oxygen is now forward. Now the methyl gets pushed back. Now this is in plane of the board, but actually that water comes in forward. Try to illustrate that here. Here's the bromonium, and it's back here in the back. Okay, remember the ring back here. It's coming back. Top carbon, methyl's coming forward. Okay, here we go. Bromine's going back, and it's bonded back twice. Methyl's coming forward. Since the bromine is back, how's the water going to come in? From the front. Okay, you come in from the front. Kicks off the bromine, but also when you come in, it pushes the methyl back. Bromine gets kicked off, the methyl just gets pushed back. Water came in from the front, pushed the methyl back. The bromine got kicked off. It's back here. When it gets kicked off, but it's still bonded to that lower carbon back. There's your outcome. How do we get that product there? Well, we just lose the H, right? Something can take the H. There's a Br minus that's sitting here. And the Br minus, take the H, electron stay behind. We get that plus what?
HBr.
Plus HBr. You also get the enantiomer. The enantiomer comes from where everything is reversed. Okay. See if we can predict the products down here. Predict the product of this first one. No stereochemistry. Do it without stereochemistry, because stereochemistry really doesn't matter here. At least not relative stereochemistry. We'll point something out, but you can actually do both of these. How does that look? I see some people shaking head yes. Chloronium ion, and then the water attacks carbon on the left, becomes more substituted. Okay. There's no stereochemistry here. That carbon's not chiral, so it doesn't matter how you draw it as long as you have everything connected to the carbon correctly. This is chiral, but there's only one chiral carbon. We can star that. It will be racemic. You can just put that in your notes for now. Racemic means it's going to be both configurations in the carbon. This one down here, this is just bromine. This is one of the easiest reactions in organic chemistry. Unless you include stereochemistry, but it's the same thing here. One carbon, it's racemic. Yes, I would highly recommend that you be able to think mechanistically so you can work out the answers. But the more you do, you can we a little bit of memorization. The memorization should come after the understanding, not before. Because if you just rely on the memorization and have no understanding, then you're going to be in bad shape. Once you get your understanding down, then you can start doing a little memorization to help speed you up. But you've got to have the understanding foundation. Questions about those two? Yes?
Both of the bromine ions bonded and that would
There's no H2.
Well, there's no water. The intermediate is the bromonium ion. Bromonium ion, if I draw it with no stereochemistry, it would be that there. You're not going to isolate the bromonium ion, although some have been. I gave you a reference to one. Something's going to open this up. The only thing you have is the other Br minus. There's no water here. This is the thing that opens it up. We're going to attack left or right. Attack over here, pick this off, and that gives that product. Attack carbon. This is backside. The problem is there's no stereochemistry here to consider. That's why I didn't show it. I mean, yes, it is tetrahedral. This bromine is either forward or back. All that, yes. But there's only one possible outcome. And so you really don't have to show it. Again, we'll learn. We'll be looking at that when we get to stereochemistry. Please do these on your own. This is the inner halogen. Same mechanism as that, but because it's two different halogens, you have regiochemistry. Is the iodine going to be on top or bottom? That type of question. And this down here is just another sort of variation of a reaction. This is DCl. What is D? Isotope for hydrogen. Deuterium. So this reacts as if it's HCl. Chemistry is the same, except you just, instead of an H, you write D. And deuterium is often used because it does allow for stereochemistry sometimes, where an H would not. So many times you'll see a reaction done with deuterium because of it allows for stereochemistry. But it's the same as if it's HCl. And that was actually a reaction we looked at 2 days ago, right? Okay, so that was halohydrins. It comes from water attacking your halonium ion, like bromonium ion. Okay, next on the outline is synthesis of epoxides. An epoxide is a three-membered ring with one oxygen. So it's a cyclic ether. But it's the three-membered ring. Called epoxide. You may have heard of epoxy glues. An epoxide, where when it's polymerized, it turns into a glue. Epoxides are commonly made from alkenes. You react an alkene with a peroxy acid. Okay, note this is not RCO2H, benzoic carboxylic acid. It's 3 oxygens. If that was only 1 oxygen, that would be a carboxylic acid. The extra oxygen is called a peroxy acid. If under my hand was an H, that would be hydrogen peroxide. H2O2. But this is bonded to the acyl group, a peroxy acid. A common peroxy acid is MCPBA. It should be in your textbook. Metachloroperoxybenzoic acid. So that's a common peroxy acid that's used. We could say MCPBA. Okay, we'll look at the mechanisms. You want to make sure that you recognize the similarities to the other mechanisms, because it will be very similar. Okay, peroxy acid. You have 2 oxygens bonded together. The one bonded to the carbonyl, well, let's look at here. If we start here, the carbonyl is polarized toward the oxygen. That pulls electrons this way, and this pulls electrons this way. Ultimately, all this pulling to the pi-bonded oxygen leaves this terminal oxygen partial plus. The last oxygen is electrophilic. That's the oxygen that the pi bond attacks. Just like when we attacked chlorine, pi bond attacked chlorine, kicked off the chlorine, yeah? Same thing here. Pi bond attacks oxygen and kicks off oxygen. Where are we going to leave cation at? Left or right? The left. Correct? Bond to oxygen. The H is also on the oxygen, so it's really a bond to OH. And what gets kicked off? This group. These electrons move on to that oxygen, become third lone pair, and that's a minus charge. Now, this new group has a lone pair. Because of that, it's going to immediately back bond, just like if it was a bromine. And when that back bonds, what do we get? We get the 3-membered ring, which is quite similar to a bromonium or chloronium. Difference is, this can go neutral by losing an H, where that has no H to lose. This can only go neutral through something attacking over here and giving the bromine its lone pair back, kicking it off. This can go neutral by something taking the H, and indeed this thing, acetate or something, acts as a base. These electrons bond to H, these electrons move on to oxygen. And what does that give? This right here gives final product. Here's your product. Epoxide, which is a 3-membered ring. And then when this takes H, you get that byproduct. So this is the case where the 3-membered ring can be isolated by losing the H through the acid-base mechanism. And that's called an epoxide. Yes, it's a strained 3-membered ring. It's strained, it's quite reactive, but they can be isolated. And then they're often used as reactive intermediates. And we'll see the chemistry of epoxides and we'll get it too. The most common way to make an epoxide is right here, react an alkene with a peroxy acid. You see the similarities in the mechanism. What did we forgot Well, we didn't forget it. What do we need to write here under this? NAF. Because as soon as this attacks the oxygen, what is the oxygen doing? Yeah, this back bonding is happening really right here, and a lot of books will show it right there. I just think that's too confusing. You understand what I'm doing here? I've done it for 2 or 3 days. I'm showing this intermediate. It's really not formed. I think it's useful just baby step. Write this. How many intermediates in this entire mechanism on the board?
2. Oh, no.
Only one right there. That's the only intermediate. That's not intermediate because that's not actually formed. If it ain't formed, how can it? You see what we're doing here? Here's the alkene, your oxygen in your leaving group. Okay? Go bond. Okay? I'm going to attack you. As soon as I attack you, you back bond. Well, you got kicked off. Okay? There was no intermediate because as soon as this bond's being made, the back bonding's happening at the same time. Right? These are concerted. This step and this step, the back bonding, are concerted at the same time. Okay, so that's the epoxide. Questions about that mechanism? What do we have here? MCPBA, what is that? That's dichloromethane. That's just a common solvent. You do need to start becoming familiar with solvents. A lot of times solvents are shown. Recognize it's a solvent. Definition of a solvent, that it's inert. It doesn't react. So you recognize it's a solvent and you just ignore it. You've got MCPBA. That's your, and what is that going to do to the alkene? Make epoxide. Right? Note cards. Product here will be boom, 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 boom. Oxygen bonding to both carbons, bam. This is racemic, but there's no relative stereochemistry, so we're not going to show the dashed and bold. Actually, it could show the dashed and bold, but it's going to be a 50-50 mix. Racemic means 50-50. I mean, you actually get a product that looks like that, and you also get a product that looks like you get both. Again, we'll talk more about that later. With rings, it's easier to show the stereochemistry. It's also definitely needed. Because here we're going to have relative stereochemistry. First show the product with no stereochemistry. Just the connectivity. Just show the product without any dashed or bold. Peroxy acid, well, that's peroxy acid, right? Just different ways to show peroxy acid. Maybe this is the easiest reaction in organic chemistry. Yeah, if you ignore stereochemistry, what do we have here? Alkene, oxygen, just right? Make a 3-membered ring onto the alkene. I mean, there's a 6, but then we made this 3-membered epoxide. But look at this. We've got stereochemistry. 2 in the plane, 1 forward, 1 back. Same thing here. If we make the 2 bonds of the ring and the plane, then we say methyl forward or back there. Can you show precise stereochemistry? We're actually going to get enantiomers. We'll show the methyl forward, show the oxygen back, and the oxygen back. This is connected here, yeah. Plus that's going to be 50-50. Those are 2 enantiomers. It all comes from this being planar, and when it attacks the oxygen, the peroxy acid could be on either side. If the peroxy acid is forward, then the bond to oxygen is going to be forward. And with the oxygen back bonds, it will be forward. So if both bonds to oxygen are forward, the methyl gets pushed back. Or the peroxy acid could be on the back. Alkene attacks back. Oxygen back bonds, both of those bonds are back. The methyl gets pushed forward. Methyl sort of default. I mean, if that's back, the methyl has to be forward. If you have 2 in the plane, 1 forward, 1 back. Okay, here's 2 others to do. These are a touch more involved because of free rotation. Ultimately, peroxy acid is going to add an oxygen across the pi bond to give you a 3-membered ring. So if we drew this without stereochemistry, it's going to look a little ugly. And it would be that there. But both of these carbons are tetrahedral and chiral, so it matters both. We're getting ahead of ourselves just a wee bit on stereochemistry, but let me show you the trick to doing these. You can also do it there, it just doesn't matter up there as much. Here it matters more. These here, I would turn your alkene before you do anything. Here the alkene is, if it's on the board, like this, okay, I'm going to turn the paper flat. Keep an eye on this carbon here. Well, let's go ahead and draw them in. This methyl coming off. When I turn the paper flat, I want you to tell me if the methyl is going forward or back. Forward towards you guys or back. Okay, here's the methyl. How's it going now?
Forward.
Yes. Okay, here it is. Well, I'm going to just turn it a little bit so the alkene is like this. See the methyl? Look at my thumb. Now forward. Okay, I'm just going to turn this that way. I'm going to draw the alkene, but I'm going to act as if it's flat and say the methyl is forward. And actually that guy goes back. That's another way to just show this, as if it's just turned 90 degrees. Now, instead of saying the reaction is over here, front or back, Now we can say top or bottom. I've turned the alkene face. If it comes in from the top, alkene attacks oxygen and its back bonds, both bonds are up. So what you can do is get rid of this and put both bonds straight up. These are better bond angles, and it shows the tetrahedral nature than this. That's kind of ugly bond angle. Now you could also redraw it and say, hey, I'm going to get rid of the pi bond and put my oxygen straight down. That's where the reagent was attacked down and back bonded from down. Okay? And your stereochemistry is already there. By turning it and then putting your new oxygen there, you get the stereochemistry you need. Do that on your own. Roman numeral 4, synthesis of cyclopropanes. Of course, cyclopropane being a 3-carbon alkane. Remember ring again. I see similarities. Two different ways to make cyclopropanes. Both of them from carbines. What's a carbine? First reagent is diazomethane. Okay? CH2N2. With heat. Here's a Lewis structure for diazomethane. Any structure you draw is going to have 2 charges. It's net neutral, but it's going to have 2 charges. This is the most common Lewis structure. Now, diazomethane is actually a toxic and explosive gas. So we won't be doing this reaction in lab this week. Actually, this week we're doing bromination of transtilbene, right? So this is a little bit, it's tedious. You got to be very careful handling this stuff. If you heat diazomethane, it will rupture in 2. Okay? This nitrogen will leave. These electrons will just break away, move on to the nitrogen. What does that give? Break away, lone pair now on nitrogen. It gives nitrogen gas, N2. You heat diazomethane, it will produce nitrogen gas. What does it leave behind? Just this species, the CH2 with a lone pair. Now the CH2 with a lone pair is actually neutral. Okay? And carbon's neutral. Carbon with H, and a lone pair. Why is it neutral? Well, carbon owns 2, 3, 4. It has 4 electrons. That's how many it's supposed to have. But it doesn't have an octet. That's not a typical carbon. It does not 4 bonds. And we said usually a typical carbon will be 4 bonds. And we said if it's not typical, it will be charged. Well, this is an exception. This is an atypical carbon that's not charged. It's sometimes called a divalent carbon because it has 2 bonds. But that is a carbene. A carbene is a carbon that only has 2 bonds, yet it's neutral. And to do that, it has to have a lone pair, called a carbene. Now, why am I showing 2 charges here? That's because it has dual character. And this is just sort of a convenience, but it's really net neutral. What's the hybridization of this? We talked about this week 1.
As we do.
3 regions, it's sp2. Okay? sp2. 1, 2, 3. 1 p orbital, right? What type of bonds do you see? Sigma bond to H, sigma bond to H. Lone pair is in a hybrid. Okay? It's got an empty p orbital. It does not have an octet. It's electron deficient, so that means it's electrophilic. It would like electrons. The pi bond, the electrons from the pi bond will add to it. They have an empty orbital. That's sort of the plus character. So this is really attacking the plus character. Just like if pi bond attacked an H+, we could attack it. So this tells us that it's got attackable character. Pi bond to carbon, we get this. Do you think this is actually formed? Well, the new thing has a lone pair. So what is it going to do immediately?
Back.
It's going to back bond. And when it does, what do you have? Product. You don't even have to remove an H. It's neutral right there. How many intermediates in this reaction? There's no intermediate here. Because that's not actually formed, right? Here's the carbene. I bond attacks, you back bond at the same time. Boom, cyclopropane. There's no intermediate. I just drew this on the board so we could. The new thing here is forming your carbene through expulsion of the nitrogen, and then understanding the reactivity, tact, back bond. There you go. Hopefully you see the similarities in the previous reactions, the ammonium and the epoxide. Another way to make carbenes, which is actually more convenient, is to use chloroform and base. This will give a carbene, but it gives the carbon with 2 chlorines as opposed to carbon with 2 H's. How do you get a carbene here? The H of chloroform has some acidity. Hydroxide will act as a base, take the H. These electrons move on to carbon. What does that give? It gives the carbanion to an acid-base reaction. The reason this is formed is because all these chlorines pooling stabilize that minus. And so that's why chloroform is a touch acidic. We can do this chemistry. But at this point, one of these chlorines will leave, like the nitrogen leaving. When this leaves, we can get chloride, but what's left behind? A carbon with 2 bonds and a lone pair. Carbon with 2 bonds and a lone pair. And lo and behold, that's a carbene. It's a divalent carbon, which is neutral. It's just like that up there, except it's got 2 chlorines instead of 2 H's. I bond attacks. At the same time, this back bonds, and so we know that's not actually formed. I'm just showing that back bonding is a second step. When it back bonds, we get our cyclopropane. Yes, 2 chlorines will be there. And so this can be called a dichlorocyclopropane. Yes, the chlorines will be there, and they will be very difficult to get rid of. But dichlorocyclopropanes can be made, this is more convenient because that's just chloroform and hydroxide. That's a lot more convenient than diazomethane. You can predict products, diazomethane. You see this, what do you think? base and fulcrum. Dichlorocarbon. I would turn this first. This one's going to have stereochemistry ring. Please do these two. We'll look at these next time right here. Okay, on Wednesday we'll look at Roman numeral 5 and 6. Please look ahead at those. Those are alternative ways of hydrating an alkene. Oxymercuration and hydroboration. I'm not sure, but we need to have a quiz. Not sure what to win. Okay, guys, have a good day.